Welcome back, everyone. This lesson continues off of the 7.2 video where we were graphing rational functions. The last video was in the form of our transformations, like as in g of x here, where you have the degree of the denominator is greater than the degree of the numerator. Today we're going to be talking about how to graph functions like in the form of this g of x, where 3x plus 4 divided by x plus 1, where our degrees of each of the polynomials in the numerator and in the denominator are both equal. So one way of doing that is to rewrite g of x into the form that we already know how to graph by transformations. So you would do this by long dividing. So when you take a fraction like 1/2, how do you write that in order to divide? You would tip it over and you'd put the 2 outside of your division bar and the 1 on the inside. So the 2 is outside, the numerator is on the inside. You pretty much tip it over to the right, and then you would long divide, add your little decimal, and you would go 2 goes how many times into 10, and you put your little decimal right above the decimal, and you would say 5, or so your answer would be 0.5. Well, we set up our polynomial long division the same way, in the same order, so that x plus 1 divided by 3x plus 4, like that. And then remember, in polynomial long division, you take your first term, your x term, and you take the x and multiply it by 3 to get 3x. So you write that above. And then you take the 3, multiply by each of the terms, and you get 3x plus 3. And then you have to subtract. And you get those cancel out. 1. So you know you have a remainder in that 1 because the degree of the 1 is less than the x plus 1. So you can write it as a remainder of 1, so plus 1 over x plus 1. So this is actually our function. Oh, that changed. Plus 1. So that's really our g of x. I'm going to flip it around. 1 over x plus 1 plus 3. So this is in the form that we talked about in the last video. And I would choose to graph this function and compare it to the parent graph of 1 over x. So we know that the x plus 1, the plus 1 on the inside of the function, moves your function to the left 1. And then the 3 goes up 3. And remember our parent graph, x, y equals 1 over x, our parent graph, it's fab 5. You've got -2, -1/2, -1, -1. 0 is undefined. That's when the denominator is equal to 0, making your function undefined. We also included a little -1/2 because that would be at a -2. And 1/2, 1, and 2. So that's 1/2, 1, and 2. And so our parent graph would look like asymptote at that x equals 0, another asymptote at y equals 0, and your parent graph would look like this. Your 2 branches in the first quadrant and in the third quadrant. So now we just have to pick it up and move it. And remember, your asymptotes go with it. So we're going to go left with the asymptote. So your asymptote moves to the x equals -1. and up 3. I'm going to erase my parent graph at this point and its asymptote. And you'll see there's no stretch or compress, just all translating. Oh, where did that come from? So there you have it. So pretty much taking what we know from the last lesson and applying it. And the only extra step is you have to long divide. So I want you guys to try this extra example, number 3. I want you to pause the video, try to work it out for yourself, and when you restart it, you'll have your answer. Hopefully you got something like this. You'll see that you can rewrite g of x into the form of 1 over x plus 2, which is a transformation to the left 2 and up 2. And make sure your asymptotes are at x equals -2 and y equals +2. So do we want to have to rewrite these functions every single time? No, not really. We really don't. What you want to take a look at is, how do I get this vertical asymptote of x equals -2? Look back at your beginning function before you rewrote it. Where do you see x equals -2? And why is it a vertical asymptote? Well, if you think about it, we've had 3 domain restrictions that we've been talking about all year. You know that when you have a fraction and its denominator is equal to 0, that cannot happen. That fraction is undefined. So if you take a look at this denominator and set it equal to 0, you'll see that x is equal to -2. And that is when the function is undefined. So we need to know that our function does not exist with an x value of -2. And that right there is what creates our vertical asymptote. Another interesting feature that we can get fairly easily from this graph is our horizontal asymptote. If you take a look at y equals 2, I see that from the very beginning g of x as the coefficients of my x terms. Now, this only works if your degree of your polynomial is equal to the degree of the polynomial in the denominator. So those have to be equal in order to use this idea. So I see 2 over 1, which gives me my horizontal asymptote. Now let me organize that information for you. I'm going to take a look over here. When we're graphing, as in example number 4, if you have degrees of your polynomials that are equal, they're both degree 1, then you have this general form of a rational function. Now, this, of course, is our hyperbola because we could rewrite it into the transformed way that we did in the last video. But what you need to know, the takeaway, is that your vertical asymptote of this graph is when your function is undefined, when your denominator is equal to 0. Highlight that. So set your denominator equal to 0 and solve. That will give you your vertical asymptote. And then to get your horizontal asymptote, you look at the coefficients on your x values. You'll see that it's a divided by c. And if you wanted to write it in the equation of a line, it would look like y equals a over c. So I would say look at the coefficients of your x values, or x terms. So when we graph, like example 4, all I really need, this is actually fairly straightforward, because once you have your asymptotes, then you just have to figure out where your function is, where the branches are. So I know my vertical asymptote is when my denominator is equal to 0. So take that guy, go x minus 3 is equal to 0. So I know x is equal to a positive 3, and I'm going to plot that. That's my vertical asymptote right at 3. I'm going to label it as x is equal to 3. And then to get my horizontal asymptote, I'll go in green. Oh, that did not change. Horizontal asymptote, I'm going to look at the coefficients of my x terms. So y is equal to 2 over 1, which therefore is just y is equal to 2. So y is equal to 2 is your horizontal. So you pretty much have the framework at this point to graph your function. Now you just have to figure out where your branches are. So my suggestion is take a look at your vertical asymptote. It's shifted over to the right 3. Now, we know all the excitement happens around that vertical asymptote for your branches. So I'm going to pick x values to the left of my vertical asymptote, and then I'm going to pick x values to the right of my vertical asymptote. So 3 points to the left, 3 points to the right, plug them in. I know that's a little bit of work, but it'll get your graph. So to the left of my vertical asymptote, I'm going to plug in maybe like 0, 1, and 2. And then I would not want to plug in 3. I already know my function is not defined at 3. So go to the right, 4, 5, and 6. So use your calculator at this point, and at 0, when you plug in 0, you get negative 1/3. Plug in 1, you get negative 3/2. Plug in 2, you get negative 5. Oops, sorry about that. X and Y. At 4, you would get 9. At 5, you're at 5.5, and 6, 4.3. So just plot it at this point. I'll erase my little bubbles. 0, negative 1/3. 1, negative 3/2. 2, negative 5. Dang. At 4, all the way up at 9, all the way up here, and then 5.5, and 6, 4.3. And then that's pretty much as I need at this point to graph these. So let's do one more quick example about this form. When you graph this function, we don't have to rewrite it. You can rewrite it, you don't have to, because all you need is your vertical asymptote, which is when the function is undefined. So x plus 2 is equal to 0. Solve that, you get a vertical asymptote at negative 2. So frame it up. x equals -2. Your horizontal asymptote is your coefficients. So y is equal to 3. Now we're going to just plug in some x values to the left of my vertical asymptote and plug in 3 points to the right of my vertical asymptote. X and Y, X and Y. So I'm going to choose my vertical asymptote is at -3. So pick the 3 x values to the left that are -3, -4, and -5. And then 3 x values to the right, -1, 0, and 1. And plug them all in. And you get a 10, 6.5, 5.3, -4, -0.5, and 0.6. So plot it all. All right, and you'll see your branches just cruise along the asymptotes. Your asymptotes really just frame your graph. Something else we should talk about is the domain and the range. So our domain is all the possible x values that could work for this function, and that is directly related to our vertical asymptote. We know our function is not defined at x equals -2. So your domain includes all real numbers except for x equals -2. That's an R. And then the range, we know, includes all real numbers except for our horizontal asymptote of y equals 3. So all real numbers except for y is equal to +3. And there you have it.